Hello everyone, I'm going to present the project I've done for the Google Summer of Code 2020 with Radare. My name is Zifan and I'm an undergraduate student from Malaysia and also a computer science major. I enjoy reverse engineering software and games, and I have been using Radare 2 for years and just started contributing to it this year. My project is mainly focused on improving the R2 debugger. The work I've done includes reverse debugging and adding support for WinDebugKD net. I've been working with my mentor Yuzi Zep and Florian Markel, and I would like to take this chance to thank them and every member in the Radare team. Let's start off with reverse debugging. Reverse debugging is the ability to reverse program execution or simply stepping backward in a debugger. We know that this is impossible on the hardware level because the state of a system is constantly being updated. However, this can be done using software to keep track of previous states and restore them. Reverse debugging allows us to view program state and control flow in history. The previous implementation of reverse debugging on R2 captures register and memory snapshots, also known as checkpoints. This supports basic reverse debugging by restoring the debugger to a previous checkpoint and continuing the program until it reaches the previous instruction or a breakpoint. However, this is hard to track the previous program counter after executing a jump instruction. This can be overcome by tracing register and memory changes at every executed instruction with index and later applying them. When stepping or continuing back, we can just look up the previous PC value or the latest PC value that hits a breakpoint. For example, when stepping back from the second instruction here, we replace the PC value with the previous instruction address at index 118. Then we apply the latest registers and memory changes before that index to get the previous value in RAX and the memory, as highlighted in red here. Reverse debugging on R2 currently supports x86 architecture, and ESIL support will also be available. Here are a few commands for the usage: to start and stop the reverse debugging session, to step or continue back, and to save and load session to and from disk. There's also a new config called debug.traceContinue. The new configuration is used to choose between tracing every executed instruction along the way or taking a snapshot at the next debugger stop, such as breakpoints. Debug.traceContinue is set to true by default to trace every instruction when continuing. Let me demonstrate the usage. Here we have a simple program that increments a counter in a for loop. We can debug the program with R2 and run until the function main. We can start the reverse debugging session with DTS+. The debugger will trace every changes in register and memory and save that for restoration later. So now we can start stepping, and the debugger will trace every changes. Let's say we want to move back to the main function, we can run continue back DCP. And now we are at main, the initial point when we start the reverse debugging session. We can also do step back here. Let's say after we call the function foo. And now we are at the place before calling the function foo. Let me show you the new configuration for reverse debugging called debug.traceContinue, which is set to true by default to trace every instruction when continuing the debugger. We can run until the function foo. We know that the function foo will increment the counter for 10,000 times. And this will take a lot of time when running in a reverse debugging session. Let's set a breakpoint at the end and continue the debugger. We can see that the debugger doesn't stop because of the overhead when tracking every register and memory changes in each instruction. We can stop the debugger and let's see how many loops have we run. So we can see that we only run almost 1,000 times. Let's say we want to skip this loop. Let's start all over again. Let's say we want to skip this loop, we can turn off the trace continue configuration to skip over the loop. Let's run until the function full and start the reverse debugging session. However, this time we must set a breakpoint so that the next debugger stop will occur, and reverse debugging will start taking a snapshot after the stop. Let's turn off the trace continue configuration and we can continue the debugger. So we can see that the debugger already reached the end of the function. And we still can continue back or step back to the previous instruction. And that's it. Next, WinDebug KDNet support. Windows allow kernel mode debugging via KD interface, and R2 already has KD support over serious connection in the past. KDNet, on the other hand, allows kernel debugging over network connections using the same KD interface. This replaces serial connections similarly to virtual KD. KDNet protocol is basically KD packets wrapped in UDP packets with extra header info. The implementation can also be found by analyzing debugengine.dll. Here is the KDNet packet structure. It consists of three parts: the header, data, and hashmag. The type in the header determines if it is a control or data packet. A KDNet control packet is used to establish the connection and set up encryption keys. The KDNet data consists of sequence number, direction, padding size, and the KD packet. The KD packet is 16 byte a line here, and the padding size is stored as pad size. The whole KDNet data highlighted red in here is encrypted with AEX 256. And the KDNet data is used to generate the hashmag with SHA 256 hashmag, but only the first 16 bytes of the hash is used. Kernel debugging on Windows using KDNet is easier to set up compared to serial ports on VM. We can run the following commands on Windows to enable kernel debugging over the network and connecting it with R2. There's another debugger improvement for R2 on Windows platform using Debug Engine, which is the backend of WinDebug. All credits here goes to the member Gustavo LCR. Debug Engine provides API to execute the same function as WinDebug commands. This allows new WinDebug IO and debug handler using debugengine.dll. We can debug programs, crash down files, remote target, and KD using the same command line parameters as we would on WinDebug.exe. Because of the use of WinDebug backend, we have direct access to WinDebug shell using IO system command. For example, here we list the backtrace and loaded modules. Thank you everyone for joining my presentation, and I will be available for the Q&A session.